Now about alternating series. So far we have seen the series which are series of positive terms. Let us see what's an alternating series. A series of the form a1 minus a2 plus a3 minus a4 plus so on, where an is greater than 0 for all n belongs to n, is called an alternating series, which is denoted by minus 1 power n minus 1 into an. That means it has alternative positive and negative terms. Each term is positive greater than 0 for all n belongs to n, but here the sign is plus minus and so on. See, for example, minus 1 power n minus 1 into 1 by n. Here, compare this with the standard form of the alternating series. an is 1 by n and minus 1 power n minus 1 as per the standard form. So when you expand this, 1 minus half plus 1 by 3 minus 1 by 4 plus so on. So this is called an alternating series. So let's see what's absolute convergence and conditional convergence. Absolute convergence means if sigma an is a series of real numbers such that sigma modulus of an is convergent, then we say that the given series converges absolutely, or it's an absolutely convergent series. That means if you have a series of real numbers or alternating series, anything is fine. Then if modulus of an is a convergent series, then the given series converges absolutely. Conditional convergence means series consisting of positive and negative terms, that is alternating series, is said to be conditionally convergent if the given series converges but summation of modulus of an diverges. In that case, we say that the given series converges conditionally. It is called as conditional convergence. And one more point to note is every absolutely convergent series is convergent, but the converse need not be true. So whenever a series converges absolutely, then the given series also converges. But if a series converges, then there is no guarantee that it converges absolutely. For example, take this series. This series is convergent. I will show how it is convergent using Leibnitz test. But now the series, assume that this series converges. When you take the modulus of nth term of this series, it gives you summation 1 by n. Using P-series test, we know that this series diverges. Therefore, this series converges conditionally because modulus of an diverges, whereas the given series converges. Now here there is a test for the convergence of alternating series, which is called as Leibniz test. The given alternating series is convergent if limit of an as n tends to infinity equal to 0 and an is greater than an plus 1 for all n belongs to n. If these two conditions are satisfied, then we can say that the given alternating series converges. The given series will not be convergent if either an is not greater than an plus 1 or limit of an as n tends to infinity not equal to 0. So you can conclude that if any one of the condition is not satisfied, then you can conclude that the series is not convergent. For example, minus 1 power n minus 1 into 1 by n. Here, an is 1 by n. Limit n tends to infinity an is limit n tends to infinity of 1 by n. 1 by infinity, it is 0. So, first condition, it's satisfied. Now, for the second condition, we know that n is less than n plus 1 for all n. Take the reciprocal. 1 by n is greater than 1 by n plus 1 for all n. So that is nothing but an is greater than an plus 1 for all n. Hence, the given series is convergent using the Leibniz test for alternating series. Now let's consider few more examples for absolute convergence and conditional convergence. See, this is the given series minus 1 power n minus 1 into 1 by n. We know that this series is convergent using the Leibniz test. Just now I explained how this series converges. Now find the absolute value of nth term, that is find the absolute value of an, that is equal to summation 1 by n. When you take the modulus of all the terms of the given series, then you will get the series as 1 by n. The alternating series will convert to positive series. We know that this series diverges using the p-series test. Therefore, if the given series converges and modulus of an diverges, then the given series conditionally converges. The given series is conditionally convergent. Similarly, consider this series. It's an alternating series. It is written as minus 1 power n minus 1 into 1 by n square. An is 1 by n square. So limit n tends to infinity of an is 0, 1 by infinity 0. Then we know that n is less than n plus 1, n square is less than n plus 1 whole square. Take the reciprocal. Therefore, an is greater than en plus 1 for all n belongs to n. Using Leibnitz test, the given series, given alternating series converges. Now you find out modulus of an, which is equal to 1 by n square. All these negative terms will vanish, just you have positive term series. Using p series test, p equal to 2 now, this series is convergent. Therefore, given series as well as modulus of an, this series also converges. Hence, the given series is absolutely convergent. Now here there is one more test for the convergence, that is D'Alembert's ratio test for the absolute convergence of a series, which is also called as generalized D'Alembert's ratio test, because if a series converges absolutely, then it is always convergent. You can check the behavior of the series using this test as well. A series summation an containing positive and negative terms is absolutely convergent if limit n tends to infinity, an plus 1 by an modulus of this value is less than 1. Then the series absolutely converges. See, for example, check the convergence of this series. This is a series containing positive and negative terms, and an is n square by n plus 1 factorial. So write an plus 1, n plus 1 whole square by n plus 2 factorial. Find out this ratio, modulus of an plus 1 by an, which gives you, do the simplification, an plus 1 by an with the modulus gives you the value 0, because here n square this cancels anyway, 1 n remains in the denominator, 1 by infinity gives you 0, 0 which is less than 1. Therefore, the given series converges absolutely. Modulus of an is convergent by ratio test.